Good day everyone, my name is Chin Kai Singh and we are from Group 7. Today we are going to present to you our filter design on removing noises from the given audio signal file. So this is our tables of content which made up of 7 parts, which firstly we introduce our team members, followed by sampling, winnowing method, DTFT, bilinear transformation, convolution, and Z transform. Our team consists of 5 members who are Ao Shiguan, Chang Yu-wei, Chin Kai Singh, Lau Shaoxuan, and Sim Zhongxian. First, let us walk through the process of analyzing an audio signal using the sampling technique. We start with an input audio signal file, typically in .wav format, which is read using the command or the read, and it will give two output, which are Y represented by signal and Fs represented by sampling frequency. Audio signal can be plotted in 3 types of domain, which are continuous time, discrete time, and frequency.
Hi everyone, my name is Chen Yue. Now I'm going to present the FIR filter design. We want to design a band stop filter by using the Blackman windowing technique in order to filter out the noise at 0.2 radian. We set the filter order equal to 100 and length of the filter is 100 plus 1. We also set that the band stop frequency range from 0.175 to 0.225. And below here show the output of the filter with the magnitude of 15 dB, and at the right you can see is the impulse response of the filter, and it shows the peak at the middle of the impulse response. Next, I'm going to show the difference in between the input signal and output signal after I implement the FIR filter. We use the method called Y equal to filter B1X, and you can see at the left is the input signal. You can obviously see that there is a noise at 0.2 pi radian. And after we implement the FIR filter, you can see the result output signal at the right. There is a noise has been removed at 0.2 pi radian. Okay, that's all for me. Let me pass to the next person.
Thank you. I'm Ao Shiguan. So I will explain about the DTFT, discrete time Fourier transform. Basically, discrete time Fourier transform is a mathematical tool that transforms discrete time signal from time domain to the frequency domain. Below will be the formula to obtain the behavior of the signals, magnitude, and phase. There are two important spectrums in the discrete time Fourier transform, which are magnitude spectrum and also phase spectrum. The magnitude spectrum tells us how strong each frequency is, while the phase spectrum shows the phase shift by using the audio signal given and the coding below. The two outputs show successfully to obtain in frequency domain as the figure shown below. The function of ABX is to compute the magnitude of the frequency domain, while the ANGX is to compute phase angle in radians of the frequency domain.
Good day everyone, I'm Sim Zhongxian, and I'm going to discuss the topic bilinear transformation. So a bilinear transformation is actually a mathematical technique to form an analog filter which we define in the S domain into a Z domain digital filter. The formula is shown here where C is equal to 2 over time sampling. In this slide, I demonstrate the process of converting an analog filter into a digital filter using bilinear transformation. The analog Butterworth bandstop filter is designed with a stop band frequencies of 0.175 and 0.225. Using the Butterworth function, we create a first-order Butterworth filter. Next, the bilinear transformation maps the analog filter into the digital domain, preserving its characteristic. We apply this digital filter to the input signal. On the left-hand side, the time domain comparison shows how the filter signal has reduced the amplitude. On the right-hand side, the frequency domain plots highlight that the bandstop filter effectively attenuates the specific stop band, seen around omega is equals to 0.2 pi radian and 1.8 pi radian. In summary, the bilinear transformation ensures the digital filter closely replicates the analog filter's behavior.
So next we are going into apply filtering using convolution. Convolution is actually a mathematical operation that combines original signal and filtering functions to produce a filter signal function. For our case is we are using the filter method command with input arguments, numerator, denominator of filter, and lastly is the original signal, and we can get output as filtered signal. Convolution can be divided into 2 parts, which are FIR and IIR. So this is our FIR filtering design using Blackman, and this is our IIR filtering design using Butterworth.
Hi everyone, my name is Lau, and now I will continue with the analysis of the filters using Z transform. Z transform is commonly used to transform a discrete time signal even system into the complex value frequency domain. It's a tool for analyzing and understanding discrete time systems, including digital filters and also other signal processing systems. Mathematically, we can get the Z transform of the system by summing all the value of the system multiplied by Z to the power negative n. And in MATLAB, we can visualize the poles and zero of the system that undergoes Z transform by using Z plane BA, where B is the numerator of the system function and A is the denominator. And in our case, we use Z transform to evaluate the system constability and also stability. In a stable system, we must see that the unit circle is inside the region of convergence ROC, and for a causal system, we need to observe that the ROC is right-handed, or as shown in the figure beside, the ROC is the shaded region outside of the circle. Next, let us continue with the FIR filter analysis. So in MATLAB, first we set out the FIR filter, and secondly, we visualize the poles and the zero of the FIR filter after the transform using Z plane B FIR A FIR. And to check stability, we also include the unit circle as reference. Since the system is a FIR system, we know that the ROC is actually the entire Z plane as at Z equal to 0. And as shown in the diagram besides, as we already confirmed the causality, and we observe that the unit circle is within the region of convergence here. So this also marks the stability. While for the IIR filter analysis, we adopted a similar approach. At first, we set the IIR filter inside MATLAB, followed by the visualization of the poles and zero of the filter using Z plane, EIR, EIR. We also included the unit circle as reference to check stability. Since it's not the FIR, we need to check the ROC externally. The system function of the filter is shown below, and the ROC is determined to be Z greater than 0.7679. So the ROC is the region outside the radius 0.7679. So this is a right-sided ROC, and the system is causal. And since the unit circle is included in the region of convergence, the system is also stable.